So, today we're going to be continuing on our introduction to modular arithmetic. So this is part 2 of our introduction. So in part 1, in our previous video, we first learned the notation for modular arithmetic, and we also learned that if A is congruent to B mod M, then A minus B is a multiple of M. And we also learned that we can add, subtract, and multiply any integer to both sides of a modular equation. And we also learned the addition and subtraction rule. So we got a lot done, but we still got some stuff to still learn about the basics of modular arithmetic. So let's start off. We're going to start off with the multiplication rule. The multiplication rule. Okay, so if we have some integer A is congruent to some integer C mod M, and some integer B is congruent to some integer D mod M, then we know that A times B is congruent to C times D mod M. So we see here we started off with the same thing that we started off with for the addition and subtraction rule. That's cool. Instead of adding and subtracting these things, we multiply because it's the multiplication rule. So this is what the multiplication rule is, but why does this work when this works? So again, if A is congruent to C mod M, that means that A minus C is congruent to 0, so it's a multiple of M. And similarly, B minus D is congruent to 0, it's a multiple of M. So let's first look at this expression. So A minus C is a multiple of M, and a multiple of M times an integer, B, is still a multiple of M. So this thing is a multiple of M. And similarly, B minus D is a multiple of M, and a multiple of M times an integer C is, again, a multiple of M. So this entire thing is also a multiple of M, which means, so this is a multiple of M, and this is a multiple of M. And we discussed earlier that the sum of two multiples of M, again, gives us a multiple of M. So this entire thing is a multiple of M, so let's remember that. So first, let's expand the brackets and simplify this expression. So A times B minus B times C plus B times C minus C times D. And we see that the B times C's cancel out. To get that, this is equal to A times B minus C times D. So this, we know that this is a multiple of M, so this is a multiple of M. So we know that if some value minus some value is a multiple of M, then those two values are congruent to each other in modulo M. So A times B minus C times D is a multiple of M. Therefore, A times B is congruent to C times D mod M. So here we proved it. We proved the multiplication rule. And this is pretty useful along with the addition and subtraction rule. So make sure to remember this rule. Let's erase that. And we're going to learn our last rule, the last rule that we're going to discuss in our introduction, which is the exponentiation rule. Hard to pronounce. Exponentiation rule. So, if some integer A is congruent to some integer B mod M, then A to the K, let's make that a bit darker. A to the K is congruent to B to the K mod M, where K is any non-negative integer. Because if it's a negative integer, if it's a negative power, then this is not going to be an integer. So K has to be a non-negative integer. So So that's the exponentiation rule. But why does this work? So firstly, from this equation, we know that a minus b is a multiple of m. And now we're gonna review our factorization skills. So how do you factorize as a squared minus b squared? Well, it's a minus b times a plus b. I hope you guys all know this. And how do you factorize a cubed minus b cubed? This is a bit harder. Well, it is a minus b times a squared plus ab plus b squared. And then how do you factorize a to the 4 minus b to the 4? Well, it is a minus b times a cubed plus a squared times b plus ab squared plus b cubed. And so on. It works like that. And then, so therefore, a to the k minus b to the k, where k is a non-negative integer, this would equal a minus b times some polynomial using a and b. So a and b, this expression will consist of a and b. And a and b are both integers, so this value is going to be an integer. And we know that a minus b is a multiple of m. So a multiple of m times an integer is again a multiple of m. So this entire thing is a multiple of m. And this is equal to this entire thing is equal to this. So this, a to the k minus b to the k, is a multiple of m. And we know that if a value minus another value is a multiple of m, then those two values are congruent to each other modulo m. So a to the k is congruent to b to the k, modulo m. So we just proved the exponentiation rule. Now, don't worry about why this works. If you expand it, it becomes like this. I'm just showing this to let you know that if you factorize expression in this form, a minus b is always gonna be a factor, which is so a minus b is always a factor, which means that this entire thing will always be a multiple of m, making this also a multiple of m, which makes a to the k be congruent to b to the k modulo m, when a is congruent to b modulo m. Sweet! We got the exponentiation rule, as well as the multiplication rule. So, let's review. Then let's review all the stuff that we learned in this introduction. All the basics. So firstly, we learned the notation. So for any integer a and any integer b, and some positive integer m, where m is not equal to 1, if a and b have the same remainder when divided by m, we can write that a is congruent to b modulo m. And we know that if this is true, if a is congruent to b modulo m, then a minus b is a multiple of m, so it's congruent to 0. It's congruent to 0 mod m. Yeah. And we also learned that you can multiply, add, and subtract integers on both sides of a modular equation. So if that is true, then a plus k is congruent to b plus, let's write that congruent symbol, meter. It's congruent to b plus k mod m, and a minus k is congruent to b minus k mod m, and a times k is congruent to b times k mod m. So you can add, subtract, and multiply any integer to both sides of a modular equation, and where k is an integer. Keep that in mind. Okay, so, and also we learned the addition, subtraction, and multiplication rule for modular arithmetic. So if a is congruent to c mod m, and b is congruent to d mod m, Then by the addition rule, we know that A plus B is congruent to C plus D mod M. And we know that A minus B is congruent to C minus D mod M. That is the subtraction rule. And we know that A times B is congruent to C times D mod M. And this is the multiplication rule. And these rules will all be pretty useful actually in competition math. Oh wait, and we forgot one more, the last one. This is the exponentiation rule, where if this is true, if A is congruent to B mod M, then A to the K is congruent to B to the K mod M. Oops. I'm so bad at writing M's. Oops. Yeah. Where K is a non-negative integer this time. So K is a non-negative. K has to be a non-negative integral. It has to be a non-negative integer here, and here K can be any integer here. So that's all we learned in the past two videos. That's quite a lot, and this may seem quite like nothing. Like it may seem pretty like not. It seems cool, but like it doesn't really seem useful. But in the next video, we're going to be using these. We're going to be using a couple of these rules to solve a competition math problem, and you're going to see that it's actually pretty useful, and it makes solutions really elegant. And yeah, that's why I like this. That's why I really like this topic. It's really beautiful. So I hope you understood all the content that I taught you in the past two videos. And see you in the next video, where we're gonna start solving problems with these rules. Ooh. Okay. So see ya, and thanks for watching, and yeah, see you in this next video.